Welcome to This Explainer. Today, we're tackling what is absolutely one of the most massive challenges in artificial intelligence right now, and that's AI memory in long visual contexts. I mean, think about it. When we feed an AI a giant collection of images, or say an entire hour-long video, how exactly does it remember and process all of that without just buckling under the sheer weight of the data? Well, let's find out. Okay, let's dive into this. Because this is essentially the modern needle in a visual haystack problem for vision language models, or VLMs. We want to ask an AI a question about a very specific event in a very long video. But finding that exact moment when the AI is trying to process thousands and thousands of frames, it's incredibly difficult.
Here's our agenda for today's journey. First, the visual haystack problem. Second, why AI attention fails. Third, the ReToken solution. Fourth, how ReToken actually works, and finally, some impressive benchmark results.
Starting off with Section 1, the visual haystack problem.
So modern AI actually understands single images perfectly fine. But if you flood it with hundreds of distractor images or a really long video, it just gets completely overwhelmed. Either it starts to hallucinate answers or it literally crashes because processing all those tokens at once exceeds its GPU memory limits. So it really becomes a retrieval problem, right? How do we select just the tiny subset of relevant frames? If you look on the right side of this visual, we have our ground truth image. This is the image containing the exact information we want. In this specific case, it's a truck sitting in the background behind some sheep and a cow. Now look over on the left. We have a distractor image, which is just a random picture of a bedroom. When an AI is asked to find that truck, but it's simultaneously flooded with dozens of distractor images like that bedroom, it gets so easily confused and completely loses track of the true visual baseline. Moving to Section 2, why AI attention fails. Let's look at the current industry standard. So, how do engineers currently try to fix this? Well, they generally use something called attention-based retrieval. But as we're going to see in full detail on this chart, it is fundamentally flawed when you apply it to visual models. Let's really break this figure down. On the x-axis along the bottom, we have the frame index of a video, basically representing time. On the y-axis, we have the AI's attention score, which is the metric that's supposed to tell us exactly how important a frame is. Now, see that vertical orange shaded column? That is the ground truth window. Those are the actual frames the AI absolutely needs to look at to answer the question. But notice that jagged orange line bouncing all over the place? That represents the attention scores. It is wildly noisy. It's spiking on completely irrelevant frames way early in the video, and it essentially completely misses that crucial ground truth window. And why does this happen? Well, it's because the AI's attention mechanism is trained to predict the next word in a sentence. It's not actually trained to actively search for and retrieve specific images.
Now, what's really interesting about this slide is the stark contrast when you compare that failing method directly to the new solution we're talking about today. This graph maps out the recall percentage, which is basically the success rate of finding the right frame, across the different neural network layers, which you can see listed on the x-axis. Take a look at the pink dashed line. That's the traditional attention retrieval we just talked about. It is basically flatlining at an absolutely abysmal average of 5.1%. But then, observe the solid green line representing ReToken. As we move to the final layers of the model on the right side of the graph, its recall shoots up dramatically, hitting 18.4%. I mean, that is a massive, massive leap. So let's see how this builds into a real architectural breakthrough. Section 3, the ReToken solution.
To really understand why this new method works so well, we have to look closely at the specific data signals inside the neural network. I want you to think of the AI's memory like a massive office filing system. Traditional attention relies on something called the query key space. You can think of this space as a really confusing filing cabinet index. It tells the AI how things are aggregated and organized, sure, but it doesn't actually know what's physically inside the files. The researchers found that this is just a terrible place to search for specific visual data. However, there's another area called the value space. This represents the actual document content. The real visual features that matter are actually stored right here. The researchers discovered that the true distraction-free retrieval signal lives entirely in this value space.
Building directly on that incredible finding, the team developed ReToken. And it's shockingly elegant. ReToken is simply a single learnable embedding, literally just one token, and it gets appended directly to the user's text question. It's trained explicitly to act as a retrieval target within that highly accurate value space we just talked about. Think of it as a super lightweight single token retrieval agent. It goes in and fixes the vision language model's memory problem without needing some massive, computationally expensive overhaul of the entire AI system.
And this figure right here brilliantly illustrates that exact difference. I want you to notice the colored bar charts on the left side of this image. Green means the AI picked the correct ground truth image of the street. Red means it completely messed up and incorrectly picked the distractor bedroom image. Look at the top bar. When the AI uses a full sentence and searches in that traditional query key space, it makes multiple errors across its layers. You can clearly see that with all those red blocks. However, drop your eyes down to the very bottom bar. When the AI uses a highly precise target phrase, like a cow, and searches directly in the value space, it is a solid block of green. It drastically and perfectly outperforms that noisy query space.
Moving right along to Section 4, how ReToken actually works. Let's break down the engineering pipeline. So we know it works in theory, but how does the code actually execute this magic? First, we have the training pipeline. Let's really trace the flow of this diagram, moving from left to right. On the far left, we input our video frames, which become those purple visual tokens. Below that, we also input our blue question tokens. Now the genius step happens right next to that. We append our single orange ReToken. All of these tokens then pass through the frozen vision language model layers. Finally, at the very end, that final layer labeled LN, the ReToken is projected out and scored using cosine similarity directly against the mean value features of each frame, represented by those green boxes. The system is explicitly trained to maximize the similarity score for the correct frame and minimize it for the distractors. And I want to point out that training it specifically in this value space isn't just slightly better. It creates a massive, undeniable performance gap. Let's look closely at graph B here. This tracks the retrieval score gap, which is basically the separation between identifying a relevant image versus an irrelevant one during the training process. The pink line represents ReToken trained in the vision value space. Notice how it rockets upward almost immediately? It converges incredibly fast and creates a much larger and way more stable gap compared to the orange line, which represents training in the old vision key space. It's night and day. Once it's fully trained, the AI uses this beautifully simple two-step inference pipeline when it is actually answering your questions in real time. Let's walk through it. Step 1, over on the left, the video is processed just once, and all of its visual features are stored in a persistent KV cache. Step 2, on the right side, the actual question is asked by the user. This triggers a first pass where our ReToken goes in and retrieves only the top K relevant frames from that cache. Then, in a second pass, the AI generates the final answer using only that cleanly retrieved data. It's that simple: retrieve, then answer.
Now, I have to stress that this two-pass system is absolutely vital to making ReToken work, and this table proves it beyond a shadow of a doubt. The traditional ReKV method actually performs slightly worse if you force it into a two-pass system, dropping from 51.2 down to 50.4. But notice the ReToken scores on the bottom row. Without the two passes, it sits at a mediocre 50.4. But when you actually allow it to first retrieve the frames and then answer based solely on those frames, accuracy skyrockets all the way up to 72.0. It fundamentally requires that highly focused second pass to work its magic.
And that brings us to Section 5, impressive benchmark results.
Let's bring it all home by looking at the hard, undeniable proof across multiple rigorous industry benchmarks. I want to break down this accuracy graph from the Visual Haystacks benchmark. On the x-axis, we have top K, meaning the number of images the AI is allowed to retrieve in order to answer the question. The solid green line is ReToken, pulling from a haystack of 50 images. Notice how it absolutely dominates on the far left side of the graph, where the retrieval budget is tiny, just 1 or 8 images. As you start to increase the number of retrieved images moving to the right, the accuracy slowly declines. Why? Because you are reintroducing distractors back into the AI's context. This beautifully illustrates a classic precision recall trade-off. ReToken simply dominates at small, highly focused retrieval budgets.
So the crucial point is really evident right here in the C equals 50 column. That means the AI is given 50 distractor context images to sift through. The standard baseline model, Qwen3VL-8B, achieves an accuracy of 58.6%. But by simply utilizing this single ReToken methodology we just outlined, the accuracy leaps all the way up to 72.0%. That is a massive 13.4-point jump when the AI is completely drowning in distractor images.
But honestly, here is where we see a true zero-shot miracle. Keep in mind, ReToken was trained exclusively on still images. Yet, as we can see clearly in this bar chart for the Video MME benchmark, it seamlessly transfers its success right over to video. Let's look at the breakdown. For medium videos of 4 to 15 minutes and long videos of 30 to 60 minutes, the green ReToken bars clearly outperform the baseline orange bars, yielding up to a 3.4-point gain. And again, this is without ever being explicitly trained on video data. It's incredible.
We can really cement this victory by looking at LV-Bench. This is an extreme long video understanding benchmark, where videos actually average over an hour in length. Using the stored cache, the baseline AI scores 40.6%. But with ReToken actively retrieving the frames, it scores 48.6%. That is an incredible 8-point improvement on hour-long videos, and it is all entirely driven by the addition of that single, highly trained token.
Now, to remain completely impartial here, we definitely have to understand the model's limitations. If we check the rightmost column for the performance delta, we see that ReToken absolutely excels at finding localized, nameable evidence. Key information retrieval is up by a massive 15.4 points, and entity recognition is up by 10.5. However, it naturally struggles when evidence is dispersed across the entire duration of the video. For summarization tasks, performance actually dropped by 5.2 points compared to the baseline. So the takeaway is that it is a highly precise retrieval tool, it's not a broad summarizer.
Which leaves us with this final thought to ponder. We've just seen exactly how appending a single mathematically precise token in the value space can completely unlock an AI's ability to search through an hour-long video and find the exact frame it needs. So if a single token can do all of this, what exactly is the next frontier for AI memory and multimodal reasoning? It's a wildly exciting space, and I really hope this explainer helped you see exactly how the underlying mechanics of it are evolving today. Thanks for joining us.